Good morning, one and all. Myself, Dr. Srinivas Bachu, Associate Professor and HOD of ECE Department. Today we are going to discuss about standard random variable, density and distribution functions, the binomial one, Poisson, and uniform distribution and density functions. First thing we will discuss about the binomial random variable. Let us consider an experiment having only two possible outcomes. Like you can take example tossing a fair coin, or whether you are sending a message from one place to another place, receiving or not, like two outcomes, receiving or not, or you are sending information transmitted or not, transmitted, not transmitted. So like these cases we are using the random experiment as a binomial random variable. So let the experiment be tossing a fair coin. Let the experiment be tossing a fair coin, I mentioned. Let the falling of head correspond to success, falling of the tail correspond to failure. Let us assume, I already told the success is not always truth. Let the probability the success be P and failure be Q. Then such that success plus failure is always unity. P plus Q equal to 1. In the above experiment, the probability of getting m number of heads and n minus m number of tails in n independent trials in a particular order is m number of heads is p to the power of m, n minus n number of tails, particular order is q to the power of n minus n. Getting head is success, that is p. Getting tail is failure, is q. Q power n minus m, p power m. This is a particular order. Like this, the number of ways to get m number of heads and n minus m number of tails in n independent trials. How many ways I can get the success m number of times, failure n minus m number of times in n independent trials in different ways is NCM ways. The required probability of the m success in n trials in any order is the probability of capital X equal to small x. The small x means here the favorable. Okay, now that is m number, that is small m, is equals to P of m. We can write shortly is equals to NCM into success m number of times, failure n minus m number of times, where m equal to start from the 0 to the n, 0 otherwise. This is called the binomial distribution at x equal to m. Now I will write the binomial distribution function of order n parameter p is fx of x equal to small m, written shortly here fx of x. This is called binomial cumulative distribution. Okay, now binomial distribution is equals to summation 0 to n ncm p to the power of m q to the power of n minus m into u of x minus m. So why I written u of x minus m? So u of x minus m means as u of x, I know it is a step function. X minus m shifted unit step function. Y means any CDF function plot is always staircase step function. Staircase step function. If you are taking here, okay now, it is a shifted unit step. We will get like this staircase step function. Draw the plot for this one. At every instant of these things. Can you take the derivative of this distribution? We will get the density function, that is small fx of x equal to summation 0 to n, same as it is. Only thing is this function is changing. Why means these all are values, it's constant values. This is your function, it's a unit step function here delta function. So shifted unit step, shifted impulse. Derivative of this step is called impulse. So delta of x minus m. So we are writing here delta of x minus m, derivative of the step function. Clear? So this is a binomial distribution and density functions at x equal to m. We will see the applications. The binomial density is applied to Bernoulli trial experiments having only two possible outcomes of any given trial. So these cases we are using the binomial density functions. Like example tossing a fair coin, whether outcome is head or tail either. Whether sending information from one place to another place, the transmitting or not, the receiving or not, or error is there or not. So that cases we are using this binomial density. It applies to many games of chance. Many games of chance. Chance is there or not. Detection of problems. Detection is there or not. In radar and sonar and many experiments we are using these things. This is applicable of the binomial the densities. Clear? But limited number of trials. Limited number of trials. That is n independent trials. Now we'll move to the Poisson distribution and density. Can you perform same binomial n independently? It's larger. It is large number of infinite number of trials, infinitely larger. This distribution can be considered as limiting approximation to the binomial distribution under the condition of the infinite number of trials with infinite small probabilities of success. It's not infinite, it's infinite small. Okay, na? It's very small approaches to zero. Like so, n is infinitely large with pre-probability, success probability tends to 0, but the product of n comma p, n trials, success probability is a constant, is noted as the lambda is a Poisson variate, lambda equal to n into p. The probability of the success for each trial, the probability for success each trial, p is equals to lambda by n. From this lambda equal to np equation we got it. Once we know the success probability, we can find out the failure probability. Failure equal to 1 minus success. So q equal to 1 minus of the success is lambda by n, the p probability. So once you got the success and failure, consider your binomial random variable with the PDF I mentioned here, NCM into p to the power of m, p to the power of n minus m. Just substitute this success and failure probabilities into the binomial, and by taking the n tends to infinity, simplify this, we will get the limiting n tends to infinity probability of x equal to m. The limiting approximation of the binomial random variable is called Poisson. That is infinitely larger number of trials with small success probabilities. That is limit n tends to infinity, a dot is there, into e to the power of minus lambda into lambda to the power of m by m factorial, where m equal to 0 to n. Otherwise, this is called a Poisson distribution at x equal to m. If you want the probability of x less than or equal to m, that is called cumulative distribution of the Poisson random variable. Now we will write the Poisson density and Poisson cumulative distribution functions. So only thing is we are changing only this function. It's fx of x equal to summation 0 to infinity I mentioned, n tends to infinity, 0 to infinity, e power minus lambda, lambda to the power of m by m factorial into delta of x minus m. By means that this is a shifted impulse train function, shifted impulse. So we'll get impulse train function like this, we'll get shifted impulse train function. So now once we got the density function, we'll get the distribution you can write. Distribution means as distribution is equals to integration of the density function. That is integration of the delta impulse is called unit step. Integration of the shifted impulse is called shifted unit step. So only thing is this is difference. Here capital F, here delta by u. So this is called my CDF of the Poisson random variable. It's a Poisson distribution function, where lambda equal to np is called Poisson variate or Poisson constant. N is called number of trials independently, it's larger infinite, approaches to infinity, and p is called success, it's whatever event of interest. So this is called the Poisson distribution and Poisson density functions. I will see the applications. It describes the number of defective units in a sample taken from your production line. Production line infinitely it's large you'll get. It's a large number, it's infinitely large. From that, a number of defective units we are estimating in a sample taken from this line. The number of telephone calls during the period of time. The period of time it's infinitely larger. The number of telephone calls arriving or number of emails to the particular Gmail account within the time interval. Then we are using the Poisson random variable and densities will get. The number of electrons emitted from a small section of the cathode root CRT in a given interval, etc. So in these cases of experiments we are using the Poisson density. Okay. Then we'll move on to the uniform random variable. A random variable capital X is said to be uniform random variable over interval a comma b if its probability density function is a constant. So fx of x equal to k over interval a less than or equal to x less than or equal to b. otherwise it is 0. So this is a my uniform random variable. It's mentioned in the things. This is a k value. I don't know the k value. Can estimate the k values. To estimate in this k value, we are using the PDF second property. From PDF second property, area enclosed by the any density function is equals to unity. Within the intervals a comma b I mentioned fx value is k, uniformly distributed. Now, since from this apply limits simplify upper minus lower k value, we got it to 1 by b minus a. The density fx of x equal to 1 by b minus a over a comma b interval. Otherwise it is 0. The graphical we mentioned here, we removed this all and we mentioned the corresponding density value, it's 1 by b minus a or a comma b. Otherwise it is not defined, and this is my probability density function, but the random variable uniform. It's a uniform random variable density or uniform density function. Once we got the density function, you take the integration, we will get the distribution. The corresponding distribution function is integral fx of x. Integral distribution is nothing but as probability of x less than or equal to a. X less than or equal to a. So upper limit is a. Like if you mention as x less than or equal to small x, upper limit is x. So what is lower limit? Lower limit you mentioned, that is over a comma b interval. So lower limit is a. We mentioned a to the x density function. Density value we got it. It's 1 by b minus a. Simplify this integration x over a to b. A to b means here upper limit is x. Upper limit is x, this one. So apply the things and simplify. Look at x minus a by b minus a. X minus a by b minus a is over a comma b interval. And when we are taking x less than a, default its value is 0. When we are taking above or equal to this, it is a 1. So we are drawing graphical representation, this thing, same thing. And x less than a, here a is there. X less than a, 0. And a to b, its value is x minus a by from this point to, right, means it's, I will take the slope, it is there, from this we will get it. Here it's b value, and greater than or equal to b, its value is 1. So like this we will get, this value is 1 and this value is here, the slope is there, x minus a by b minus a, this part will get. And mention the x-axis and y-axis values, then you can see the graph, that is uniform distribution function plot, it seems. And it describes its application here, the error quantization. In the digital communication theory, the error of the quantization part, we will see the error of the signal samples prior to the encoding in digital communication system. The quantization amounts rounding off the actual sample to the nearest discrete quantum levels. Like we will take here any is there, it means we will take the round up values, we will mention the graph uniformly, we will mention. The quantization error introduced in the round off process are uniformly distributed. So these are the applications in the digital communication system. The quantization process, we are using uniform, the random variables. The today's session we discussed about the binomial random variable, Poisson and uniform, their applications and distributions and densities we mentioned. Clear? Thank you. Any doubts you can contact to the mail hodec@mlradium.ac.in. Thank you. Bye everyone.